how basic cell works, right? SRAM cell. Okay. Now you need to know everything like how read operation works and write operation.
Just give me the brief, like as an introduction, so that I can connect. Like I go
Um,
and revise, and then I will come back to you.
okay.
Like a
Yes.
short description, like 15 minutes, not more than that.
हम्म, ये स्क्रीन
Okay.
शेयरिंग कैसे करते हैं इसमें?
ऊपर आता है ना शेयर,
शेयर।
शेयर करके बटन
अच्छा,
होगा,
ओके ओके, हाँ हाँ।
फिर वहाँ पे स्क्रीन शेयर होगी।
हाँ ठीक है। विजिबल।
हाँ विजिबल।
वन नोट दिख रहा है ना?
हाँ
Like you studied SRAM cell, like you know working.
हम्म।
Then I'll just simply you got to know how the ratio is being done, cell ratio and this
Like through logical effort.
logical effect, not logical effect. Actually, I mean, let me tell you. You have this access transistors, right?
हाँ या।
Access transistors. This will be turned on by word lines.
हम्म।
Entire row will be turned on, and this is another cell, adjacent cell.
What is like output based kind of thing.
So in a row, entire row that row cell will be on. If you have
Mm-hmm.
32 by 32, entire
Mm.
32 cells in that row will be turned on.
Mm.
So basically, what happens is there will be bit lines,
Mm.
and usually when you are writing data,
Mm.
let's discuss about read operation. Then we'll go to write. Read में क्या
Mm.
होता है कि like this is an back-to-back inverter, right? If you
Mm.
store 0 here, then it should be 1 here.
Mm.
So if I let's say I have grounded both the bit lines, what would
Mm.
happen? This side is 0, this bit line is 0,
Mm.
and this word line is turned on, and this as well. There
Mm.
won't be any current flow this side, right? Because there is
Mm.
no potential difference.
Potential difference zero.
Yeah. But here you have 1 and you have ground here. So electrons
Okay.
would be flowing this way. So there is a current here.
Mm.
So this bit line है ना, ये bit line.
Mm.
Every
Capacitor is there.
yeah, every wire has some capacitance, and
Mm.
not only that wire capacitance, you even have a column cell. Like in this column, you have a
Mm.
cell underneath this SRAM cell. This is one cell,
Got it.
you have another cell here. So this
Got it.
column bit line will be connected to another word line transistor.
Mm.
So this diffusion cap is also there. So
They will be
all
in.
together they will resemble a some finite capacitance. You have pre-charged it to ground. Now it is charging up actually. It is actually charging up to VDD.
Mm.
And this capacitor is actually ground only, because this is also connected to ground since there is 0.
Mm.
So there is no charging of this capacitor.
Mm.
So with these bit lines, I can give this to a sense amplifier.
Mm.
So this sense amplifier detects the potential difference. Like this has, let's say V, and this has closer to V. I mean, let's say V is 0 volt.
Sense amplifier is made of op amp.
Differential amplifier. Differential amplifier.
Differential amp.
Yes,
Differential amplifier. No?
yes.
Ah,
So let's say this is 0 volt, but this is not
ah,
0
got it.
volt.
Got it.
Yeah. So thus we get the output here.
Difference output.
Yeah,
If
yeah.
there is a difference, then we will get output. If there is no difference, we don't get any output.
Yes. We mainly do this because actually we can wait here. Like,
We want to keep those both bit lines to be at the same potential. That is the
mm,
main agenda.
no, what I'm trying to say is, uh, you have 0 and 1 here, right?
Mm.
If you can pull out this wire and consider this as an output, I can say that this bit line is 0. I can
Mm.
directly say that it is 0. And if it had been 1 or 0, I would have said that this output is 1.
Okay.
But actually, this bit line itself is not a ideal wire. This is not a
Mm.
ideal wire. It has some capacitance.
Mm.
So in order to charge this up, this capacitor, bitline capacitor, it takes some finite amount of time. So, but in memories, we do not have that much of time to read each cell value, right? It should be फट से होना चाहिए. Like it should
Mm.
be some Mbps of speed I need to have. So for
Mm.
that,
Quick.
I will be turning this SRAM cell for a very few fraction of seconds. Some from,
Okay.
let's say, some nanoseconds. So
Okay.
in that nanoseconds, it's really difficult to charge this up. So that's why we use a sensam to detect the small voltage drop on this bit line, which is compared to this line. That is why we use sensam. And this is the read operation. Why we actually pre-charge it to VDD, not ground.
Yeah.
That will take some time to explain. We'll come to this again after write operation. राइट ऑपरेशन में ये होता है कि ओके दिस इज SRAM cell. Now I need to write, let's say, I have a data. I have the data 0 and 1 here. Now I need to write 1 into this.
Mm.
So actually this is my output. I consider this as my output or
Mm.
the memory that is stored in SRAM cell. So it is 0 and I need to store 1. So what I would do is I'll charge this to, let's say, ground. Let's say ground. This is to VDD.
Okay.
So what would happen? Like this is ground. This capacitor is grounded, and actually this
Is
SRAM cell
zero.
consists 0. That in the sense this NMOS is turned on, ground kiya tha. So there is no current flow here,
Mm.
and this is VDD. This is charged to VDD, and this is also connected to VDD via PMOS. And here also there is no current flow. Actually, there is no write operation is being happened here.
Mm-hmm.
So whenever, since uh, given that this node is considered as my output or uh, memory of the SRAM cell,
Uh,
whatever you wanna write into this SRAM cell, write
mm.
the data into this bit line. Since you have considered this as your output, yeah, input, whatever you call, SRAM cell का
Hmm.
memory element, memory bit.
But what if I go with the other one apart from it?
uh, Nothing would happen. Like you need to consider this as your memory element, like
Okay, I have to
information,
consider anyone of it.
any one of
Both.
it. Yeah, because there would be conflict when you have a sense amp here.
Hmm.
You have to take the output from one of the pin, right? Like
Hmm.
in sense amp, what happens is you have a similar structure. You have a back-to-back connected inverters, and this is connected to a NMOS, where this is controlled by a sense amp enable control pin.
Okay.
Okay, you know differential amplifiers, like how
Uh,
do they work?
uh,
So this is PMOS, this is bit line, this is bit line bar. So let's
hmm.
say this is VDD and this is VDD.
Barnet, so it should be ground.
One second. Let me put it down here. ये क्या हो रहा है? Let's say 0 is stored here, 1 is stored here. What I'm trying to say is, if you have fixed this as your information node,
Hmm.
let's say there is 0 stored in this node, 1 here, and you are trying to read the data from this SRAM cell. Hello? Hello?
You're audible.
Yeah, like you have disconnected or me?
No, no one has disconnected, maybe because of the internet connection.
Okay.
It happens.
So yeah, there is 0 and 1, and you precharge these bit lines to VDD, and you turn on this word line. And usually these two control pins are same. So initially this will be 0, that in the sense this bit line is connected to this node, and this bit line is connected to this node,
Hmm.
and you have 0 here, and this is connected to this node via PMOS, and here you have 1, and it is connected to this node via this PMOS.
Hmm.
So what happens is, since it is like these two are VDD and this side is 0, then there will be discharge, right, in this left side.
Hmm.
Either to VDD or 1, there is no potential difference and there is no charging or discharging. You got it?
Huh.
This
Hmm.
one, I am referring to this one.
Hmm. Like the below cell which you have drawn later
Yeah, this is
is the
actually
like
sense amp.
sense sense amplifier, no?
Yes, this
Basically.
is this entire thing.
Okay, got it.
Yeah. So
Got it.
this is PMOS. Sense enable is 0, and this is turned
Hmm.
on. This is
Okay.
also.
Both are turned on
Yeah, and you have access to
and
this sense amplifier. But the thing is, sense enable is 0, so this
this
NMOS
is
is
off.
off. So there is no connection to ground.
Hmm.
So ये तो you will have a diffusion cap right here
Uh,
and diffusion cap here.
hmm.
So there is no actual potential difference between this SRAM cell node and this bit line, right? This bit line.
Okay.
So there is no. drop in the voltage. It would remain at
हाँ,
VDD.
VDD and
Yeah.
VDD वो तो
So ये
normal
तो
है.
zero है.
हाँ,
So there will be drop here, because this
हाँ,
entire thing is connected.
हाँ.
So we will just talk like this sense enable will be uh, enabled within fraction of seconds, very small time.
Okay.
So within this small time, we will have a small voltage drop here, not uh, not up to VDD. It is more close
Mm-hmm.
to VDD. This node is actually VDD.
Okay.
So now what happens is this NMOS has something close to VDD. This NMOS has VDD. Okay, you got it. Like this is back to back connected. This
हाँ,
node is VDD and it
VDD.
is
हाँ,
connected this way.
हम्म,
So this NMOS current है ना,
हम्म,
this NMOS current is very high because gate voltage is VDD,
हम्म.
and this NMOS current is
Low.
comparatively low than this one because its gate voltage is not VDD, it is close to VDD.
Hmm.
So since this sense enable is 1, it is connected to ground, right? Now it is on. This sense enable, I have since
Change.
sense enable is initially 0
Now it's on.
and I have changed that to 1. So this transition from 0 to 1,
Hmm.
that delta t is the time. Like uh, uh, I enable the wall line at time equal to 0. Wall line is on and sense enable is 0 actually. So you have a path here. This path to here. ये तो clumsy हो गया क्या? समझ रहे?
समझ रहा हूँ. One thing like
हाँ
SRAM का जो आउटपुट है
हाँ.
वो कनेक्ट हो जाएगा ना प्रॉपर जाके सेंस एम्पलीफायर के साथ.
Yeah, I am coming to that. We are almost there.
Hmm.
हाँ. So यही होता है. ये तो on हो गया and
Hmm.
this, since this current is very high, this left transistors, this node gets to 0 very fastly than
Hmm.
this one. So
Hmm.
if this node gets to 0 first, then this PMOS would have turned on, right?
Hmm.
So this node actually gets 1. इस साइड में 1 हो जाएगा, this right side. Okay,
Okay.
so ये तो 1 हो गया, then it will turn on NMOS of this one.
Okay.
So this will become 0 this side.
Yeah.
So initially what you have in the SRAM cell, you have 0 and here 1.
Hmm.
Now on this side only you got 0.
Hmm.
So this is the thing. If you have stored information 0 on the left side, you will
Hmm.
get that information on the SRAM, SenseAmp on the same side itself.
Hmm.
So this left and right side is fixed. So in that same way, you write the data accordingly. Like you have a write circuit. It is very simple. You have inverter chain. You have input data, and this
Hmm.
is your bitline bar, and this is your bitline, and this is actually connected to SRAM cell.
Okay.
So let's say your input is 0, this will become 1, this is 0. So that's how I have written 0 here and 1 here.
Mm.
Got it?
Yeah,
Uh,
got it.
yeah, like let's say if I have changed this, uh, I have drawn like this, and my input is here. If my input is 0, this will be 1, this will be 0. This wouldn't have been 0, it will be 1. This is 0.
Mm.
So
Mm.
here there is a conflict. So now it is 1, it is 0.
Mm.
So it's actually you fix either one side, either left or right.
Mm.
Then write the data, uh,
Opposite side.
not exactly opposite. What I mean to say is, while reading, you read the output from SenseAmp. How we read is, you just pull out these pins,
Mm.
these internal nodes, and give this to a
Mm.
latch, this latch.
Okay. Okay.
So what happens is, this is, let's say, Q, and this is not Q.
You.
Let's say SenseAmp Q. This is SenseAmp Q bar. Actually, I want this as my output. This node. This node is my output.
Mm.
So if this is the information that you want, then that will be reflected here.
Mm.
Okay, and this is reflected here. So you take this as your output. Since you have fixed that left side of the cell is my information,
Mm.
and you have read that from the SRAM cell on the left side, so that is fixed.
Mm.
So you need to write in such a way that your information is passed on to the left bit line. So if I have given 0, then I would get 0 here and 1 here.
Mm.
So
Mm.
it shouldn't be like the other case. You have not and other not. This is connected to this one. So if you have given
Mm.
0, 0, it would have become 1, it would have become 0.
Mm.
So what I'm trying to say is, while designing write circuit and this SenseAmp, just check where you want to store the data in SRAM cell. If you fix left node as your information bit, then design
Give it
accordingly
right.
the write circuit.
Right. Right.
टेस्ट
Circuit.
या उल्टा हो गया तो तुम्हारा इंफॉर्मेशन उल्टा होगा, क्योंकि ये
Ah.
SenseAmp and write circuit won't agree with each other.
Mm.
This is read and write cycle, and for this, uh, like I have said, there is a delta T to turn on the sense enable. So this signal actually comes from a self timing circuit. There will be some word line replica, cell replica, and all those things, and you'll get the SenseAmp enable.
Okay.
That is like, that will take some time to explain. Is this clear?
Yeah.
Yeah.
Yeah. This is clear. This like
Like,
all these things are in those videos. No,
yes,
you
yes, yes.
upload.
Everything is there.
Arun.
Anuj Grover.
Ah,
Hmm.
Anuj Grover.
Yes, yes. Um, Actually, there are several SenseAmps. He has explained around four, I guess. Like in each
Okay.
and every circuit, there will be some drawbacks. It actually depends
Okay.
on
Okay.
PPA, whatever you
What is
want,
people?
PPA, power performance and area. If you
Okay.
want
Fine.
less area, you'll use some sort of circuits. If you want performance, you'll use some other circuits.
Mm-hmm.
So For our project purpose, we could actually just demonstrate how the read operation occurs and write operation occurs. And self timing हो तो वो बढ़िया होगा.
So you haven't tested the self timing right now.
Actually, my self timing circuit is working, but
Hmm.
I have to change this delay, word line delay and cell delay. They are not
Okay.
actually matching with the actual SRAM cell.
Okay.
Yeah, so design तो हो गया, but delay तो थोड़ा adjust करना पड़ेगा.
Hmm.
Or, or is there anything left? Like
No.
hmm, why do we actually use self timing? Is you would be having some other like external clock, right? Which is coming
Hmm.
from CPU, which
Hmm.
might be running at some gigahertz.
Hmm.
So if I like usually those clocks will be coming from PLL.
Hmm.
If I want to give this clock to this entire SRAM cell
Hmm.
and do that, what do we say? If I route this clock using some
Hmm.
H tree, some other clock tree synthesis, कुछ होता है ना?
Hmm. Hmm.
So
Hmm.
this will become very hectic. Like you wouldn't get uh, routing का area होता है ना
Ah,
metal wire.
got it, got it, got it.
Yeah, that will be huge, and there will be
Hmm.
some. Uh, Even if I like, let's say one clock is driving this entire SRAM cell, and it has to take care of the ALU and control unit, all those things. Like this clock, PLL clock का burden बहुत ज़्यादा बढ़ेगा. It
Hmm.
has to cover all sorts of things. So what, and
Hmm.
even actually SRAM actually works even at higher frequencies than the clock that is being generated externally. Like we can
Hmm.
access SRAM at really fast pace. So it would be
Hmm.
better if we could able to generate a internal clock within this SRAM itself, so
Okay.
that by itself it can generate some control signals like sense enable and
So
all.
this is happening right now in the industry. No? They are generating some self-timing circuits.
Yes, self timing circuit is everything. If you are able to
Like earlier it was like HT kind of thing. No? But as
H
the size of the chip is shrinking right now, so because of that, the distribution, the routing purpose, and the placement of the wires is getting difficult.
yes, definitely. That is the reason they have introduced this self
Mm,
timing.
mm, So that they can give a small area to into that chip, and they can just generate a clock, um, or like
Uh,
based on the which block you want to
Actually, it's not a clock.
run at which
Yeah,
like
yeah, you can say clock. Like it
it
will be generating some
yeah
pulses
it
of sense
no
enable.
no it is like you will get a clock from a source, but it
Hmm.
will automate that clock frequency based on that block which like that block what kind of
Hmm.
frequency that block wants
No, actually,
actually.
what happens is I have studied DRAM, right?
Hmm.
Yeah, उसमें क्या होता है कि like you have CPU, like you are mentioning that uh, there will be some external clock, and it is difficult to route this external clock all over the SRAM cell and access the data out. Are you saying this?
Mm, no, no. Like
Uh,
for operating a single block in a CPU,
Single block in a CPU. Which block?
like any block, like ALU block or control unit, anything.
Okay. So why don't we use that same clock to SRAM to access data?
Because you want a small period of time, na? You just
Small period
want
of
to
time.
like
Okay,
so
small.
small period of time refers small period of time refers to high frequency,
Yes. So
so that it will become fast, as like SRAM consists of
yes,
like cache memory.
I heard about frequency multiplier. We can multiply
There
with.
there will be some other things also. Yeah, frequency multiplier is one thing.
Uh, so yeah, basically what happens is like, yeah, at the end we will be increasing the burden on this clock, which is going to ALU control unit and all those things.
Mm-hmm.
It would be better if we have a separate clock for this within this.
Mm-hmm.
So there won't be any wire delays and signal integrity will be बढ़ जाता है. If I use this external clock, there will be lot of wiring and there will be lot of capacitance.
Mm-hmm.
Yeah. So what happens is CPU is connected to SRAM
Mm-hmm.
and SRAM is connected to DRAM.
Mm-hmm.
This is actually an external thing. There will be some interface and this is connected to hard disk, your secondary storage, HDD, SSD, whatever. So whenever there is a like CPU request for a data here, like it sends out some address. SRAM में check करता है, it will check in the SRAM. If it is a mess, it will go to DRAM. In DRAM, instead of picking out that particular address data and sending it to SRAM then to CPU, first it will send this actual required data to CPU. Since we have this word line activated, right? This entire row cells can be accessed because word line is on. So what we do is uh, we we basically just uh, like you know this in memory array we have row decoder and column decoder.
Yeah, yeah.
Yeah,
2.5D technology.
yeah. Some address lines are given to this row decoder and some lines to this
You're just
column.
activating a single bit in the memory.
Yes, yes, yes. So this row decoder activates entire line like
Hmm.
this row. So instead of uh, taking out this data and sending it to CPU, we make benefit out of this that fact that this word line is on. We just take the adjacent cell data as well, these data as well, by just changing the column address. If you like, this will be clear if you study the column decoder how it is actually designed. It is actually simple, like it will take very less time to switch from one column to the other column. It's not like a row decoder. In row decoder you have NAND, NOR and NOT, like some 5 stage gates will be there and the delay is so high, its logical effort is more and there will be some branching as well. Whatever you have studied in Rabaisa's lectures, that will be helpful in this decoding part. So this row decoding takes a lot of time than this column decoding and shifting to the adjacent column. Column has actually transmission gates only. So it's easy to turn off these gates and turn on other adjacent gate easily. It takes no time. Some finite amount of time, but very less compared to this row decoding wala part. So anyhow, we have selected this word line. We'll just instead of taking this data, we actually take the entire row and place that in SRAM. So this bringing out of the data of entire row is called burst mode. Burst. Instead of
Okay.
single, you uh, suck out burst burst of data.
Mhm.
So इसकी वजह से you will reduce the kind of you are exploiting spatial locality,
Mhm.
because we know that adjacent address would be having related data,
Mhm.
right? Adjacent data will have related data. So instead of taking this data, if we have taken entire row, it might come handy in future. If CPU asks for next address, let's say previously you have accessed X, now you need X plus 1. Then you need to again go to DRAM, and again you need to row decode and select the word line and select the cell, and you need to get the data again. So instead of
Mhm.
doing this again and again, you basically exploit spatial locality and you will bring entire row. Thus you have SRAM, thus you have the entire row data in SRAM and you can access easily.
Mhm.
So that is why we use this, like, why did we actually started this discussion? Yeah, why we have self-timing, right? So
Mhm.
when we switch from one column to the other column, we need to enable the sense enable signal. Like sense enable has to be 1.
Mhm.
And before reading out the data from sense amplifier, this has to be off, right?
Mhm.
If you know the differential amplifier concept, you would understand that while reading, this has to be turned off. There should be no ground connection.
Mhm.
So you need to enable this sense amp again and again. This will go turn off, on, again and again. So
Small
this,
period of time.
yeah, very, very small. This is where you have this high frequency of memory access. This column switching is really fast. And for that, you need really fast sense enabling timing, like clock pulse, you can say. That
Mhm.
that is where the self timing comes into picture. That is it. If you study DRAM and then this virtual memory, whatever this SSD, STD virtual memory होते हैं ना, actually in cache memory itself he explains why we uh, like what is miss rate, what is hit rate. While explaining those
Mhm.
concepts, he will
Mhm.
take out this burst mode.
Yeah, burst mode is there.
Yeah, so with burst mode, we exploit spatial locality and we place the data in SRAM so that the future addressing locations will have a more hit rate. We can access it from SRAM itself instead of going to DRAM. कल डिस्कस कर लेंगे, अभी तो यही है SRAM का सेल्फ टाइम.
हम्म, वो ठीक है। मुझे ये है
हाँ.
ना कि डिजाइन करने से पहले एक लेक्चर देखो।
हम्म. इसमें लाइक, हाँ, देख लो एक बार. Like I forgot to mention cell ratio and those things. You could actually watch
योर
those. Yeah, this has
हाँ
some
वो
width.
हाँ वीडियोस वीडियोस
Uh,
में देख लूंगा।
this has some width. So there has to be some ratios to get the
प्री
proper write
प्रीचार्ज
operation.
प्रीचार्ज प्रीचार्ज
Precharge,
सर्किट का एप्लीकेशन
precharge circuit, precharge circuit.
application like where are using features.
Yeah, precharge is actually used in read operation.
Okay.
So you just connect bit lines to this PMOS, and this is VDD. And let's say I have given this control to PCHG. some pin. So whenever I lower this PCHG, this bit line
It
will
returns.
charge to VDD.
Hmm.
And while reading, it has to be like both the bit lines has to be VDD, right? So
Hmm.
simply I'll connect this to this PMOS itself. But you need to think overall. Like these bit lines are running all over the SRAM cells onto SenSAM, right? There
Hmm.
is only single bit line. This is bit line and this is bit line bar.
Hmm.
So here you have simply short circuited them. In
Hmm.
read operation, it's okay that these two are
But in
VDD. Yeah, in
right
write
operation
operation,
should
there
be
will be an
open
issue.
circuit.
Yeah, so
Open circuit it should be like.
you separately connect to another PMOS,
Hmm.
same pin.
Hmm.
And this might have an issue because let's say this is bit line and this is bit line bar, and there are some SRAM cells here, and these are connected through access transistors. Let's say you have read, let's say, no, you have written some data, let's say 1 0 into different columns, like bar you have written 1 only. So what would have happened is this diffusion cap has been charged to VDD or close to VDD. This
Hmm.
diffusion cap, this diffusion, this diffusion. Diffusion in the sense there is a NMOS transistor, access transistor. This one, I'm talking about this one. So this diffusion cap has been charged closely to VDD, and the other cap
Hmm.
is actually grounded. Got it? Because
Yeah.
there is zero here. Now instead of reading, अभी तो बंद किया read operation. Now I need to
Hmm.
like write operation बंद
Right.
किया, sorry. अभी तो read कर रहा हूँ.
Right band होगा.
Now if I
Hmm.
connect the bit lines to VDD via PMOS, and this also, this is PCHD VDD. So again, timing is the key. I need to recharge these bit lines to VDD as fast as possible. इतना जल्दी
Hmm.
हो सकता है उतना बेटर, क्योंकि इसके बाद आई नीड टू enable the SenSAMP as well. Like
Hmm.
now if I charge this to VDD, then I will enable the word line, then I will enable the SenSAMP and I will get the data. So this process
Okay.
has to be fast. If this has to be fast, then VDD charging up the bit lines to VDD has to be fast, right?
Hmm.
Yeah. Let's say I have given very minimalistic time to charge these bit lines, and somehow this bitline bar has not given enough time to charge to VDD because these diffusion caps are grounded actually. I'm grounded in the sense previously it has been written again and again to zero. So these diffusions are not really charged as these diffusions. These
Hmm.
diffusions have already charged to VDD or close to VDD. So this actually takes less time to charge to VDD, this bit line.
Right.
इसका तो it wouldn't have reached VDD, somewhat close to VDD. So this is a problem. In read operation, you need both the bit lines to be at same voltage because
Hmm.
those bit lines are given to SenSAM, and this SenSAM is actually enabled for a very short time to get high frequency of uh, reading of data. This SenSAM will be enabled for a very short time period. Okay,
Hmm.
so this is actually close to VDD, and this is actually VDD. And let's say mm, one is stored here. Not yeah, one is stored here, and left side you have 0. Okay,